It's actually an innovative concept in the new dams technology. CM dam is preferred over the CGD, the concrete gravity dam, due to economic advantage and simple construction. And also, it locally available material reduces the construction costs. For the stability of the CMD dam is generally designed only with compressive strength. Because of the strength of CMD is relatively low, the allowable compressive strength of CMD is the ultimate compressive strength divided by the safety factor, and the maximum pressure imposed on the soil at dam 2 must not exceed the allowable material compression stress of CMD foundation. It is a comparison between the CMD dam with the STD, as you see, and in the graph of the right-hand side, you see the clay content of the soil with the cement with a single treatment, with the lime and cement with double treatment and the clay content, and also with the cement content as you see in the graphs. The differences in the required strength, as you see, the right angle triangle dam, the maximum sigma C is 1.97. However, for the trapezoidal dam, that is CSG dam or the CMD dam, the maximum sigma C compression stress is 1.13. That is comparable to the triangular dam. The design variable for the trapezoidal dam of CMD or CSG is dam height, friction coefficient, crest width of the dam, bottom width of the dam, factor of the whole deviation of the upstream face, and upstream side slope, downstream side slope, as you see in this figure. These are the governing equation of the optimum shape of CMD that should satisfy the stress of dam hill, a safety factor against sliding, and principal stress of toe that we derived it as the new job for this work. By sorting the calculation result of more than 7 million trial combinations with Monte Carlo simulation, the probability distribution of the friction coefficient, the dam height, and the crest width of the dam corresponding to different corrected trial combinations in analysis of the stability of dam were obtained. And the range of upstream slope of the CMD is from 1.4 to 1.9, and the downstream range is 1.1, 0.3, and 1 to 1. For the minimum friction coefficient of a CMD, that the minimum corrected trial is 0.0, the optimum bottom width of the dam reaches to, for the example that we have, is 685 meters. One of the most important aspects of geotechnical problem is to adopt a suitable constitutive model for the material that I'm showing the CSG, the concrete, and the rock material. As you see, there are many constitutive models which can be mainly grouped in two categories: nonlinear elastic models and elastoplastic models. 4 constitutive models of soil have been chosen into elastic and plastic model groups, were used in the finite element analysis for comparison of numerical results and proposing the more flexible model in the static and dynamic analysis of the CSG dams. These models are or include the Duncan and Chang, Morcolon, Duake-Prager, and Harding soil models. And we have analyzed with these models, as you see for the Morcolon, for the Duncan Chang, Zuckerberg and Harding story models. And after that, I'll bring the result for the stress strain curve. As you see, for the non-associated Drucker-Prager model, as you see in this graph, is so in the agreement with the experimental test that has been done in the lab. Is the other results that you see. And the upstream dam slope reaches a minimum value of 0.4 when the downstream dam slope is 1 to 0.8. And various concepts and ideas were discussed in an effort to establish a line of separation between the CMD and RCC dam types. Damages to the heel of the CMD were less severe than those to the concrete gravity dam, and the stress concentration in the upper part of the dam was eliminated for CMD. Thank you for your attention and thanks for listening. Okay, due to the limited time, I forced to finish my presentation. I'm waiting for Dr. Wieland to start the presentation. I sincerely hope that you will enjoy today with the debate and networking, although it is virtually. And thank you for the participation. And I'd like you all to take a look at the agenda with me. At this stage, I would like to introduce Dr. Wieland to start his presentation. And the title of the presentation is Our Higher Seismic Safety Standard Required for Dam Forming Dam Cascade Along River. It is very interesting subject because of the cascade dam that although many papers published for this one, but it is very interesting that proposed by Dr. Wieland. Dr. Wieland, the floor is yours, please.
Load the pre-recorded presentation.
Okay, sir. Okay, I will play. Okay, Mr. Martin, you can start now. I hope you see your presentation.
It is pre-recorded, so you have to run it.
Okay, okay. Once you say, I will run it.
Dr. Wieland,
Gentlemen,
Probably
my
they
name
don't
is
have the recorded
Miran, and I'm
message.
from
It's better that you can start now with
Zurich,
yourself.
Switzerland. Today, I would like to talk about the following subject: are higher seismic safety standards required for dams forming dam cascades along rivers? This is a subject which has been discussed in recent years. Okay, what are the special seismic safety aspects of dam cascades? Basically, as a failure of any dam in a dam cascade may cause overtopping or failure of a downstream dams, and since the probability of failure of any dam of a cascade is larger than that of a single dam, the question comes up whether dams of a dam cascade need higher seismic safety standards than single dams. And I would like to try to answer this question. Now, dam cascades are quite common. Here is an example shown along the Rhone River in France, starting from Lake Geneva to the Mediterranean Sea. There are about 20 different dams, mainly run-of-river power plants. Okay, and the question is, of course, if one of these dams fails, what happens, and do we need higher seismic safety standards? Similarly, in Southeast Asia, if you look into the Mekong River Basin, which is here in the north, is in China, followed by Laos, Thailand, Cambodia, and Vietnam. And as you see here, a number of dams have already been built in the upper reaches of the Mekong River, and there are several dams are planned in the middle reaches of Mekong, forming large cascade over distances, I would like to mention here, of several hundred or even 1,000 kilometers. Now, if you look on a map, how such rivers can be developed, that is a picture from Iran showing the Karun, Kherson, and this river. And I would like to show you, this is a simplified sketch of this cascade, Kherson River, Karun River here. And if the dam fails, of course, it has some consequences on all dams further downstream. I've also shown in this map, if you have a possible earthquake occurring somewhere, I would say the area of strong ground shaking is quite limited. If you have a long cascade, of course, not all dams will be affected by the earthquake ground shaking. As we can see here, if we take this area of strong ground shaking, the red one, we can see there are about 4 or 5 dams which will be exposed to strong ground shaking. Now, what happens if, let me say, if you have a failure of one of the reservoirs, we may have overtopping of the downstream dams, which may be concrete dams or which may be embankment dams. Here is a picture shown from the Wenchuan earthquake, 2008 in China, where a run-of-river power plant has been overtopped. And as we can see here, basically nothing has occurred to this concrete structure. Of course, also since the reservoirs there have been quite small and the overtopping depth has been small. However, if you have major overtopping of run-of-river power plants, then we may have a stability problem, okay, which has to be taken into account. Otherwise, if you have a small overtopping heights, basically nothing occurs to these dams, to the safety of these dams. On the other hand, if you look into a large arch dam, this is a Vaillant arch dam, 262 meters high, where in 1963 a large rock slide occurred and which caused basically a replacement of the reservoir and a big wave with the depth of over 100 meters over flooded the crest. And as you can see here from this picture, basically this photo, a recent photo, as you can see, not much has occurred to the dam crest, except here at this location, where at the left bottom, where we have some local damage at the crest. In general, we can conclude based from this experience, if you have overtopping of large arch dams, basically these dams will not fail, as this example here has shown. On the other hand, if we look into embankment dams, if an embankment dam is overtopped, also only a few, let me say, less than, say, 2 meters even, as in the case here of the Tom Sook concrete face rockfill dam. In the US, it eventually causes progressive failure and catastrophic release of the reservoir. So therefore, we can conclude that embankment dams are vulnerable to overtopping and are quite likely to fail. Now, what are the earthquake effects of dam cascades? A strong earthquake may affect several dams of the dam cascade at the same time, but the ground motion, I think that is obvious as I've shown before, will be different in every dam site. Only few dams will experience the strongest ground motion, which has been assumed in a seismic design of a dam. Of course, the epicentral distance of a dam site. In general, we can say the weakest dam will fail if the ground motion is the same. Now, the worst case scenario in a dam cascade is basically the failure of a dam with the largest reservoir, especially when it is the uppermost one of a cascade. All dams below will be overtopped in the case of concrete dams or fail in the case of embankment dams. Now, the question is, what is the probability of failure of dams? And here we have to consider two approaches. The first approach is a deterministic concept of seismic safety assessment of dams. Here, the seismic design criteria are as follows. A dam must be able to resist the strongest ground shaking to be expected at the dam site, which we call worst case earthquake scenario, which is also referred to as maximum credible earthquake or MC. Therefore, based on this concept, dams cannot fail, and therefore no stricter safety criteria are required for dam cascades. So if we design for MC, basically there is no reason that we use stricter safety standards. However, we know there are a number of uncertainties in seismic safety assessments of large dams. They are as follows. Number one, the seismic hazard and the earthquake ground motion. There are large uncertainties involved, especially for the strongest earthquakes. Number two, we have large uncertainties in material properties and also material models for concrete and embankments material. Number three, also there are uncertainties in the assumptions made in the seismic analysis of the dam, with especially dynamic interaction with the foundation and the reservoir and seismic wave radiation. So there are a number of uncertainties if you do a seismic analysis of a dam in a deterministic analysis. Now, if we look in a second one, the probabilistic concept of seismic safety assessment of dams, there basically we calculate the probability of failure, which is a basic requirement. It is very difficult to calculate the probability of failure of dams, because all of them are unique, so you would have to check one by one. Often for the seismic safety assessment of dams, probabilistic analysis, so-called fragility curves are used, which describe probability of failure as a function of, for example, peak ground acceleration or other ground motion parameters. But these are not suitable. Why so? Number one, it is not possible to characterize the earthquake ground motion by a single seismic parameter. Most damage mechanisms in dams depend very strongly on the duration of strong ground shaking, which is not reflected by peak ground acceleration or spectrum acceleration or any other parameters used in describing fragility curves. Number two, there is also a problem in defining the failure limit of dams. The worst failure scenario, of course, is a catastrophic release of the water from the reservoir during or even after the earthquake. And also the calculation of the inelastic seismic vulnerability of dams is still a great challenge. Analysis models that consider only a single ground motion parameter, therefore, are too simplistic. Now, if you look into the seismic vulnerability of dams, I would say this is the most important factor, I must say, to be considered if we think about the probability of failure. I would like to show here on the left, this is a failure of Sarajevsk Dam in Albania, which in 2009 was subjected to magnitude 4.1 earthquake, resulting in a PGA of 0.07G. And as you see here, the dam was severely damaged. The reservoir was not released. On the other hand, if you look at the Aratosawa Dam in Japan, which was subjected to a magnitude 7.2 earthquake in 2008, with a peak ground acceleration of 1G, which did not damage. So therefore, we can say well-designed dams and well-constructed dams can be very safe during very strong earthquakes, whereas poorly designed, poorly constructed dams will already fail during small earthquakes. Here I'm giving a short example of a cascade here of the Upper Mekong River in China, and I would like to discuss here what are the worst failure scenarios. It is obvious in this cascade consisting of several large dams, and if this dam fails here, it's a large reservoir, this Kiowan Dam, it will overtop all the other dams. The Kiowan Dam is a concrete dam, whereas here Nushadu Dam is also a very large project. It's even a larger reservoir, is an embankment dam, and it will most likely fail if it will be overtopped by the water released by Kiowan Dam. Also, if the Nushadu Dam will fail, here it will basically affect these dams further downstream because this reservoir is really very huge. It will also have an effect on the whole downstream flow of the Mekong River down to Vietnam, as I've shown before. Now, what are the critical failure scenarios of dam cascades? Number one, we can consider, of course, depending on the cascade, we can consider a number of failure scenarios. Number one, which I would like to list here, is a failure of the lowest dam. In this case, it is obvious the reservoir volume of the lowest dam will be released, okay, and I would say the damage which may occur or the consequences are quite limited if it is not the largest one. Second one, the failure of the uppermost dam, if you assume that, and all downstream dams are concrete dams which can withstand overtopping. Okay, the damage is also not very, is not the worst case. Number three, failure, the same one, failure of the uppermost dam, and all downstream dams will fail due to overtopping because they are, for example, embankment dams, which will fail. So let me say this will have a more catastrophic consequence. Number four, failure of a dam with the largest reservoir, and all downstream dams are concrete dams which can withstand overtopping. So basically, the consequences would be similar to over failure of this largest reservoir. And other failure scenarios with dams that can be overtopped or dams that fail due to overtopping reservoirs with different volumes can be considered. In general, I must say the worst case is the failure of the dam with the largest reservoir. Now to come to the conclusions of this, let me say, analysis, which is described in my paper, we can say, number one, no higher seismic safety standards are required for dam cascades, but all dams of a cascade should satisfy the same seismic design and safety criteria. Secondly, to reduce the risk of the consequences of dam failure, that is a flooding, and dam strengthening would only be second priority. Number three, it is of dams due to earthquakes, as a seismic hazard is a multi-hazard, which besides ground shaking also includes possible effects of faults in a dam footprint, rock falls and landslides, impulse waves in the reservoir, and others, which have to be considered in this probability of failure analysis, which is usually only done for ground shaking. Number four, seismic safety includes safety during and after a strong earthquake, which requires safe operation of a reservoir after an earthquake. This is very important. Finally, I would like to mention, if somebody would like to use higher seismic safety standards for dams or for dam cascades, this of course is not forbidden. So thank you very much for listening to my presentation.
Thank you so much, Dr. Wieland. And I'm asking for the next speaker, Morimasa Tesuda. The title of the presentation is Operation for the Selective Water Intake Account of downstream water temperature and turbidity. Mr. Morimasa, the floor is yours, please. You are going to present? Nakomara? Mr. Nakamura. Hello?
Mori.
It's not yours? Oh, okay, okay. Probably is not here. The third one, the third presentation is backwater effect and compensation due to dam one power project in low PTR, and the presenter is Nakamura. Professor Nakamura is the deputy manager of the Kansai Electric Power Company. Please, you can start.
Hello. Can you hear me?
Yes, yes, please.
Can you
Yes,
show? Yeah, can you show our video presentation?
you can upload.
No, I will show you. Which name, sir? Which name? Please tell me.
Thank you.
He's going to upload for you.
Takahisa Tabuchi. Is
Yeah,
that Takahisa Tabuchi?
right.
Okay.
Thank you.
A video or a presentation? Which
Yeah.
one?
Video presentation, please.
Presentation. Okay. Not a video.
Video, please. Yeah.
Video. Okay.
Yeah.
Done. I will play.
Chairman, this is Tabuchi, Kansai Electric Power Company. I would like to make presentation about the establishment and the implementation of the emergency action plan on the Namnia One hydropower project in Laos. According to the Federal Emergency Management Agency in USA, the EAP is a formal document that identifies the potential emergency conditions done and special actions to be followed to minimize loss of life and property damage. The EAP includes the notification flow chart, response process, responsibilities, preparedness activities, inundation map, and additional information. In the guideline, some case having damage on the asset along the downstream river course introduced, and it is recommended that the EAP is uniform with other EAPs that are managed by national level agencies. There exists 9 villages along the Namnia River, as shown in left figure. Total of 1,600 households and 8,500 people are residing. The villages are located near the river, as shown in right figure. They rely on the wells for drinking water due to deterioration in the quality of river water, and it is rare to use the river water as irrigation because their main cultivation style is rain-fed agriculture. Fishing is not popular because of the decreasing yield, where in the past people lived mostly on boats for transportation amongst villages, especially during the rainy season. Since the construction of the Namnia One project, access road most transport is now by road, and boats are now mainly just used to access farmland across the rivers. To facilitate this minimum water depth, allowing boats traversing the river is maintained according with the concession agreement. I would like to explain the example of the implementation of EAP and issues in Laos at Project X. Had not disclosed the inundation map since residents are likely to panic when emergency events did occur, many residents did not get notified because contact person had not been given essential information. At Project Y, some of the saddle dams were overflowed by hydraulic gradient in the large reservoir during the flood event. There, also, it took time for the flood to propagate from the upper reach the downstream of the reservoir, and the event couldn't be prevented by control spillage. Now, Project Y is updating the flood prediction simulation to control the reservoir water level during the floods. At the Project Z, one of the saddle dams breached gradually over roughly 24 hours period. It caused substantial damage because while residents were notified of the event, they did not know how to evacuate effectively. It must be ensured that they will have an appropriate understanding of the EAP. NAMNIAP 1 management plan is shown. It is divided to operation plan, inspection plan, maintenance plan, deterioration diagnosis, environmental plan, and safety plan. EAP is one of the safety plan. Okay. In order to identify conceivable emergency events, a few scenarios are considered. For each of these scenarios, risk levels are defined and relevant actions are allocated. These definitions have been temporarily set based on the practice in other projects during the construction phase. However, they were adjusted according to the actual behaviors of the dam, as suggested by NNP1 subsequent review by the Dam Safety Review Panel organized by twice in accordance with the guidelines set out in the EAP, and each time mitigations were taken and appropriate measures were taken. It is judged that the plastic movement of the dam foundation closely corresponds with repetitively rising and lowering the reservoir water level. The items to be monitored and their frequency and determined along with the period convergence of dam behavior, and dam behavior are monitored and evaluated by the NNP1 staff daily. The example of the application of damage along downstream river course, the way of the precaution is different from each project. For example, discharge test and the prevention from the entering are not conducted in some projects. NNP1 conducts the precautions of damage along downriver course carefully based on the example of other projects. The warning is conducted using the speaker on the car before the discharging. The warning is conducted from the dam site to downstream village. In addition, the signboard was installed at the downstream of the dam. This figure is inundation map. In case of the design flood, 10 hours from the start of the flood discharge amounting to 3,000 cubic meter per second occurs, resulting in inundation at the middle river course, which is the maximum inundation after 28 hours as shown in left figure. And after 48 hours, the inundation turns on convergence. and is reduced to below 0.5 meter at the middle river course as shown in right figure. From the middle to downstream, the river course will be widely inundated with 1 to 2 meter depths and partially with 5 meter depths. However, around the confluence with the Mekong River, no inundation occurs. The figure shows the inundation map of the confluence with Mekong River. It was found the Mekong River flood has much impact around the confluence with the Mekong River, so that it is necessary to share information and discussion with related agencies on how to mitigate this area. The notification flowchart is shown in left figure. According to the agreement with the Lao government, the NNP1 does not have responsibility for notification and evacuation residents. However, the NNP1 is making the effort to work cooperatively with the Lao government. It is key that special attention is given to elderly as well as to the less mobile and to mentally impeded persons. So they will have an understanding of the EAP and that where necessary special agreements are made to ensure they are evacuated. Therefore, NNP1 conducted the explanation of evacuation and the evacuation drill. Okay. In conclusion, first, in order to identify conceivable emergency events, various scenarios are considered, and for each of these scenarios, risk levels are defined, relevant actions are allocated. NNP1 has established the method to notify the dam operation with a timely and appropriate manners. Third, when usual movement is found, the quick response, such as investigation, evaluation, and measures are also required. Fourth, it is found the Mekong River flood has much impact around the confluence with the Mekong River. Therefore, information sharing with Mekong River Committee is necessary. Fifth, evacuation drill is important and it was implemented in 2020. Okay, this is my presentation. Thank you for hearing my presentation.
Thank you so much for the presentation, sir, and the case study
This
of
is
the
Kazuchi, Kansai Electric Power Company. I would like to make
Okay.
presentation about
Takashi-san.
the establishment and the implementation of the emergency action plan on the Namonia Power Hydropower project.
Can you stop? Thank you.
Yes. And for the nice presentation, especially for the case study on the backwater effect and considering the flood system. Okay, I think that there is no one attended the meeting, and we have to finalize it. MNC, there's nobody here, and therefore we have to finish this session. I'm correct? Hello? Mr. Nakamura and Dr. Wieland for your attendance at this session, event of the symposium. APG Symposium, and I really appreciate for the participation and presenting the paper. Apparently, I have to finish this session. All the best.
Okay, so shall I stop this video call, sir?
Yes, yes, yes. Thank you.
Okay, okay. Thank
Thank you,
you
man.
so much.
And thank you for your support, man.
Thank you, sir.
Thank you. Bye-bye.